Hello and welcome to this first video on proof. You need to know three methods of proof for A-level maths. 1. Proof by deduction. 2. Proof by contradiction. And 3. Proof by exhaustion. In this video, we're going to look at the first, proof by deduction, otherwise known as direct proof. I want to go through 6 examples. Here's the first. Before we can start, we need to know how to handle odd and even numbers. If a question says x is even, we know x can be written as 2 times n. And if it's odd, we can write x equals 2n plus 1. But that's not enough in a proof question. We have to state that n must be a whole number, an integer. To speed things up, it would be good to use set notation and to write n is a member of the set z, where z is the standard notation for the set of all integers. Back to our question. Square numbers. Numbers like 1 squared, 2 squared, and so on. So consecutive square numbers are numbers like 4 squared and 5 squared, and their difference is 9, which is an odd number. We have to prove that this is true for all consecutive square numbers. If we take two consecutive numbers, n and n plus 1, where n is an integer, then their squares are n squared and n plus 1 squared, and the difference between them is this. Expand the bracket, cancel the n squareds, and we have 2n plus 1, which we know is odd as n is an integer. And that's our proof. Here's our second question. Prove that the product of any two odd numbers is odd. Let's call the two odd numbers 2p plus 1 and 2q plus 1, where again p and q are both integers. Then their product is this. Multiplying out, we get this. And taking a factor of 2 out of the first 3 terms, we have this, which we know is odd. Why? Well, since p and q are integers, so too are p plus q, p times q, and n. And we have our proof. Here's our next question. Sometimes it pays to start by taking a look at the target. X squared plus y squared is greater than or equal to 2xy. If we subtract 2xy from both sides, we have this. And hopefully you'll recognize the left-hand side is a perfect square, which must be greater than or equal to 0. So here we have the makings of our proof, but it's in reverse. So we can start by stating x minus y all squared must be greater than or equal to 0 for all real values of x and y. Then multiply out the bracket, add 2xy to both sides, and we have our proof. Here's our next question. Again, let's get a feel for what's going on. Odd integers. 5 squared is 25, which is 1 more than 24, a multiple of 8. 7 squared, 49, 1 more than 48, which again is a multiple of 8. And 9 squared, 81, 1 more than 80, again a multiple of 8. Our starting point for a proof is that x is odd. So we can write x equals 2n plus 1, where n is an integer. Hence x squared is this, which gives this. We're happy to see that plus 1 term, so let's factorize the first 2 terms. Now n times n plus 1 is the product of 2 consecutive integers. So one of them must be even, which means their product must also be even. In other words, we can write n times n plus 1 equals 2 times y, where y is an integer. Hence we have x squared equals 4 times 2y plus 1, which gives our target answer of 8y plus 1. Here's our next question. Again, let's have a look at what we have here. 4 squared is 16, which is 1 more than 15, and 15 is 3 times 5, so that's of the form 3k plus 1. 5 squared, is 25. 1 more than 24. Again, it's a 3k plus 1. 6 squared, 36. 3 times 12, it's of the form 3k. 7 squared, 49. 1 more than 48. That's a 3k plus 1. 8 squared, 64. 1 more than 63. A 3k plus 1. 9 squared, 81. That's of the form 3k. Hopefully that will give us some ideas for our proof. If we call our integer x, then we could say that all possible values of x divide into one of three groups. Case 1 is where x is a multiple of 3. Case 2, where there's a remainder of 1 when we divide by 3. And case 3, where there's a remainder of 2 when we divide by 3. Let's look at each case in turn. So in case 1, x equals 3n. So x squared is 9n squared, which is 3 times 3n squared, which is of the form 3k, where k is 3n squared, which must be an integer. In case 2, x would be 3n plus 1. So x squared is this, which simplifies to this, which can be factorized to give this, which is of the form 3k plus 1, where k is 3n squared plus 2n, which is an integer. In case 3, x equals 3n plus 2. This time, x squared gives this. And now we can split that 4 into 3 plus 1, and then take the factor of 3 out of the first 3 terms, which is of the form 3k plus 1, where k is 3n squared plus 4n plus 1, which is an integer. Hence we've shown that in all three cases, x squared is either of the form 3k or of the form 3k plus 1. Here's our last example. Again, let's try and get a feel for what we have. We're told that k is a non-zero constant. So let's try putting k equal to something convenient like 4. That would give y equals x squared plus 4x plus 16, a quadratic. And we want to show that y is greater than 0. Hopefully we'll spot we could complete the square to give this, which means that y is greater than or equal to 12, which means y is definitely greater than or equal to 0 for all values of x. Out of that, we can now see how to create a proof. We need to complete the square. So y is our quadratic. Completing the square gives this. Combine the constant terms and we have this. Hence we can say that y is greater than or equal to 3/4 of k squared, which means that y is greater than 0 for all values of x as k is not equal to 0. And that's our proof. I hope you found some of that helpful.